and thank you for the team for inviting me here. It's been quite stimulating to see other dimensions to our problems. I think it's been useful. I'm going to get through quite a bit, but I think it's useful for you to perhaps to know about where I come from. I have a little background in land cover and land use. I did an agricultural science degree, first degree, and then a PhD in computer science, where I was looking at automated systems for updating land cover, land use maps from satellite imagery. But really, I've been working with all kinds of data. I work with social media data, I work on transport data, I work with remote sensing data. I've got PhD students looking at flooding, looking at wilderness, wildness, and the common thing that links across all of these things is that all the data I work with are spatial. Okay, and so really what I think I have to offer here is, yes, I know a little bit about agriculture, I know quite a lot about land cover and land use, but what I really know about is spatial data. And I think the thing that's interesting is not to me in this workshop is there hasn't really been too much conversation about data. We've had some talks here on scale and things like that, but I think when I talk to my students, and I'm in a school of geography, and geography's much the sort of qualitative human geography is a little bit like kind of not very good sociology, and the quantitative geography is like not very good maths, but the thing we have to offer, and this is what I say to my students, look, as a geographer, we've got a few things that we have to offer. We're all using spatial data, whether it's on our phones or on our applications or even old school paper maps, driving with my dad in the car with an AA road atlas. And all of those things are, essentially what we're doing in that data is representing the real world. It's not the real world. I'd love to have a one-to-one model of the world in my computer, but I can't. I think I'd go to. Well, I wouldn't go to molecules. I'd go to blade of grass. That'd be fine, But we haven't, and so part of our roles as geographers, I think, is to understand how we represent the world and what that means for then our analysis. And some of that's related to scales, and we used to just talk about spatial. And I will, but increasingly we're having to think about temporal scales as well. And the reasons for that, as I'll show in a minute, I'll say in a minute, I'm going to say it now, is, we used to say that all data are spatial, they're collected somewhere. Well, they're all spatial temporal. They're all collected at somewhere and at some time. And the where could be not just a GPS coordinate, it could be at a supermarket. Every time you use your kind of debit card, people like me are analysing that data. Okay, people like me are helping, so Sainsbury's and things like that work out whether they should sell more Wellingtons here or more kind of Red Bull there, that kind of stuff. All right, see if this works. So I'm going to just pick up on some of the things. This is my little preamble. I'm going to talk a little bit about the MORP, which actually comes from the ecological fallacy. I was quite surprised that I've not heard mention of actually the ecological fallacy, which was from the 1950s, and really, what it kind of, I'll give a little illustration. I'll also show how you can quantify how different processes operate over different scales. I'm going to use this with a little subcatchment, some subcatchment data here, and this is somewhere in China from some work we've been doing in the last couple of years. And there's about 700 data points there, approximately about 100 metres apart. And it's only in China you get this kind of data. And what they've done is they've kind of collected soil samples, and I'm just going to look at them, just essentially, for argument's sake, look at a model of total nitrogen percentage, and I'm going to use some explanatory variables to show that. And I'm going to show the variations in the answers you get. Okay, and I'm just also comment on how they interact. I can go one better on the MORP. Actually, if you can go and get the original CatMog edition of the Modifiable Area Unit Problem, 1984. I actually happen to have a paper copy on my shelf. I have very few bits of paper in my office. And although we've had lots of conversations, there's been lots of talk about the MORP in this session, I've not really seen much on it here. And essentially, as has been illustrated earlier, what this says is that the patterns and the processes are observed at any scale will vary depending upon the scale of the observation. And what this means is that your kind of inference from your data, that your conclusions you draw, and therefore if you were to plug in your data into some kind of optimization or something like that, they'll also vary as well. Okay. All of the CatMog series are available. Do a little search on the Royal Geographical Society. You can get them all there. It's a better link it's a better image on my computer. So here's my 700 data points. Let's just throw a regression at it. The data's been transformed a little bit, so I can use all the percentages in there. And we can kind of generate a model of trying to predict total soil nitrogen. And we can get some, we can look at kind of like the residuals, and we can look at how these different terms relate to our target variables, If I then aggregate that data over, I think in this case, a 250 metre grid, we get very different values. So here, if I was to kind of be looking at, let's say, the relationship between, clay percentage and my target variable, so let's have a look here, at 250, I'm getting a kind of relationship of 0.15. When I just look at the raw data, that's halved. And if I go again, it changes again, it actually flips to negative. So never mind what the kind of the R squareds and the residual and the P values are. Actually, the relationships I'm identifying between processes are varying because of the scales I'm looking at them in, and not just varying, they're sometimes flipping sign. Okay, so so how you bring your data together is quite important. Okay, another way of thinking about this is that it's not just how you bring your data together, what's your sampling frame, it's also understanding, as Laura was talking about earlier, was that different processes operate over different scales. Now, I'm not going to get into a geographically weighted argument here. It's essentially geographically weighted regression is a spatially varying coefficient model. There's lots and lots of arguments about whether it's good or whether it's bad, but fundamentally they come down to what your belief system is. Okay? If you believe there's a global truth out there and that you're trying to find the model that fits everything, okay, don't use GWR. Okay? But if you're interested in spatial heterogeneity and you're interested in process heterogeneity, then it's very interesting. And there is a variant of GWR called multi-scale GWR. There's a number of original papers, that's one of them. You can go and download the software. There's lots and lots of R packages to it. But what this does is essentially, I'm still trying to predict total soil nitrogen, but what this does then is start to look at how the different predictor variables, how they're spatially related to that target variable, okay? And if I do that, I can see that some of my variables are incredibly local in their effect. I've just picked a point in the middle of this to show and put a kind of a buffer around that. But essentially what I'm getting out then are bandwidths. This is a very small catchment. It's only about 4 kilometres, 3.5 kilometres north and south, east and west. And we've seen that some of the processes operate incredibly locally. So here this is operating over sort of 300 or 400 metres, and some of them are global. Okay? So do we know, when we're bringing our data together and we're trying to think about our model inputs, okay, are we understanding the spatial variation in the processes and the relationships in the processes that we're examining? Okay, and of course these things will interact, and they will not, I'm not going to say any more of, I have seen some of this here, they will interact in space and time, and critically, they will interact in different ways for different kinds of decision makers, whether it's a planner, a farmer, maybe policy, and maybe community. Okay, so different communities have different sort of end users. If we think about end user trade-offs, they're going to have different scales of interest and influence. Right, so that was my kind of preamble. That was my little bit of sort of Geography 101. I'm going to start with my conclusions. I'm going to talk. This is where I'm going to end up. Okay, I'm going to say that in terms of spatial and temporal scaling, I think we understand spatial processes quite well in life and in data. If I think about where the pubs I drink in, they're all filled with people a bit like me. That's not coincidence. We all cluster together. Many processes operate in the same way. I think we're increasingly, all our data is going to be not just very large and not just spatial, it's also going to be temporal. And I think one of the critical things then is when we go into that data, is that we kind of try and match if you like, the periodicity of the observation with the phase of the temporal phase of the process we're trying to examine. Okay. And I don't think we can, I think in the spatial terms, we can assume spatial autocorrelation. That is essentially a distance decay argument. Okay, that's why we have hotspots, clusters, in both social and environmental processes. I'm not sure we can do that without knowledge with temporal data. Okay, with some things, many areas, I'm thinking of hedonic price, house price data, serial autocorrelation is very heavily used. Lag data are just inputted in. But I'm not sure, unless we understand the process we're looking at, that we can just lag data and chuck it in. I'm also going to say there's a whole world of representational issues that are important. I'm going to talk about accuracy, and I'm going to talk about semantic uncertainty, what it is when we mean when we say, oh yeah, bog. What's a bog? What's a forest? Okay, and these have implications for our modelling, and there are methods for handling these. Okay, I'm going to go from spatial to temporal, and I suppose as a geographer, my credo is that I don't expect things to be the same everywhere. I'm always looking for clusters, hotspots, and I'm interested in how and where processes and relationships, how they vary spatially. I see myself as a little bit of a spatial detective. Okay, my job is to kind of go, there's something going on here, I wonder what it is. And the classic example that brought me into this was a relationship between crime and unemployment in post-coal mining areas. Okay, essentially, if you looked at all of these areas all together, as unemployment went up, crime went up. Now, some places, some coal mining areas, it didn't matter how much unemployment there was, crime didn't change. And in some areas, it didn't matter how much really unemployment there was, crime was always high. So why is that? They're very, very similar areas. They're very similar in terms of the demographics, the people that live there, all kinds of metrics. And it was actually to do with different community structures that weren't in the data. So part of our job, my job as a geographer, is to kind of go, oh, there's something else going on there, and to point that out to people who've got domain knowledge. So in statistical terminology, what I'm interested in is spatial non-stationarity and process spatial heterogeneity, and this is what's Tobler's first law of geography. And in quite a boring paper in 1970, don't really read it, what he did was he was looking at the decay of Detroit, and he was looking at the kind of neighbourhoods in Detroit and like how sort of various metrics of kind of like unemployment and deprivation, and what he did is he kind of did that classic, got them in a matrix, and he just ordered the matrix and realised that the neighbourhoods were all adjacent to each other. So the ordered matrix generated, and so it was a throwaway line. Okay, everything is related to everything else, but near things are more related to each other. Okay, so all data is spatial, they're increasingly temporal, and I think this is only going to continue. If we think about our kind of, whether it's the IoT, I don't believe the hype of 5G. I think autonomous vehicles is a waste of time. We won't go there. Ubiquitous sensing, but also our kind of everyday digital connected GPS-enabled lives. Okay, and this is changing the nature of spatial analysis, but I think while the role of proximity is well established, we think about distance decay, birds of a feather do flock together, it's less certain for temporal processes. It's good for some, carbon dating, glottochronology, I had to look it up. and the seriation in archaeology, okay? And I think we can't necessarily assume that temporal processes behave in the same way as spatial ones, that serial autocorrelation cannot be assumed. Yesterday, for weather, it's quite good. You know, yesterday's quite a good predictor of today's weather, but it's not for all things. And that's because processes have periodicities which require the timing of the observation, if you like, to be linked to the phenomenon we're observing, okay? And I think we need to think about approaching our spatial temporal data in an informed way, and this comes out of work I've been doing looking at machine learning. And machine learning is great if you've got all data, but it's not if you haven't. Okay, these two slides. So what I had here, which I should have checked this slide, I had sunspots going in a lovely kind of usual way. Okay, and you can predict sunspots, but not if your sample is irregular. So that's missed off that slide. So I think from spatial to temporal, I think the key point is that we need to have an understanding not only of how our processes behave in space, but also in time, and also the interaction in space-time, and that we've got the data that's capturing that. Okay. Now there are some lessons from the remote sensing community, and it's not very often I say this. I usually kind of start my talks with the guy going, oh, the remote sensing community, when are they going to join the 20th century, never mind the 21st? But actually they've got some things to show us. And this is, I've been working with Mike Walder, who's a big cheese in Canadian forestry, really nice chap, and we've done a few bits of work together. And essentially what's happening in remote sensing is we've moved from this time when, if you just think about land cover and land use, this is your typical kind of land cover sequence. We've got these static maps, okay, these kind of snapshots of land cover over time. We're not really doing that anymore now in kind of big school remote sensing. What's happened is that they've moved from these kind of snapshots and these, if you like, these inventories, to just working with a data cube, where at the back of the data cube you have an inventory, you have your land cover map, and then you've got all of your kind of satellite imageries all lined up, pre-processed. You can trace pixels through time, and they're examining pixels and how they're changing without necessarily changing the label. Okay, so occasionally they'll change the label on a pixel, but really what they're doing is they're looking in the space-time cube at processes. Now whether that could be things like disturbance, changes in condition, changes in quality, and so on. Okay, so really what they're doing is looking at spatio-temporal processes in their data. Okay, and Mike's paper was showing the coverage. This at the moment it's mostly in North America and I think a little bit down here, and this is the anticipated coverage when they get round to it, and this is for 2015, so there's kind of 950 images, 1,000 images in each of those locations. Okay, so lesson one for remote sensing is that really, if you think about how they're treating this data cube, rather than generating snapshots, is they're kind of looking at the signal and linking that to the spatio-temporal process in order then to pull out information that's relevant to their needs. Okay, so even when they're not changing the label in land cover, so something may still be forest, but it's changing its conditional quality, that's what they're capturing. So they're going into the data in a much deeper way. Lesson two is actually, because they're foresters, the Canadian Forestry Service is really kind of not looking at too many things. It's looking at forestry and rangeland and fire, and okay, but they've got an understanding of the processes that they're looking at. Okay, so you can't, again, I come from a world where I'm writing papers now that are saying, yeah, machine learning is great, but how's it going to learn geography? You know what I mean? And basically my answer is it has to be told. You need to think about how spatial-temporal processes are captured in the data, how they interact, and my argument is that data-driven approaches, especially just if you're trying to generate insights, come with health warnings. A quick example from Mongolia of this. I've been working with some Mongolian livestock data. It's great. I haven't put the website link up, but if you go there, if you go to the Mongolian Statistics Service, you can get all kinds of data. It's really interesting. And what I've done was just look at livestock counts over 27 years, over some counties, and essentially what the aim was to kind of look at can we predict NDVI from changes in livestock, and what happens if we add more time in, what happens if we spatially and temporally lag data, how do things occurring nearby in space and time relate to the process of interest, okay? This was chucked into a long-term LSTM neural network, and what I was trying to do was predict NDVI, okay? And essentially what I'm going to do is just look at how different combinations of spatially and temporally lagged data, you know, generate kind of, you know, improve or don't improve model fits. I'm not going to, so there's my data, the shading's all gone, which makes me worried, and I think if we look at the outcomes here, these are the results. So over time, if we look at, you know, so if we just look at temporal lagging, we can see that if we, yes, last year's data is quite good, a drop off, boof, what's happening up here? Why is 20 years ago data a really good predictor of this year? Okay, oh, I don't know what's happened there. And if we go to, you know, but there's something happened here. Okay, so I'm not really too sure why that is. We'd expect this to decline. Why is that increase? Why this drop? Well, there's a similar kind of pattern in the spatially and temporally lagged approaches. And really what we found was that these were years when there were what's called ZUDs in Mongolia. And the ZUD is when there's these extreme winters where even the Mongolians perish and all their livestock perishes, and people decide to abandon their farms and go move to the city. So there was something going on with the temporal process that wasn't, you know, cattle and agriculture is obviously linked to human decisions that wasn't in the data. So I suppose what I'm saying is that if we were to just do a straight analysis, we would have missed some of those things. Okay, so really then the key there is to think about how the timing of observations link to the temporal processes we're interested in. Now I'm going to get into my kind of last 10 minutes. I'm not going to keep you from your lunches, but I'm going to talk about land cover and land use, and I'm going to talk about two critical concepts: accuracy and I suppose conceptualizations and semantics. Okay. There's a few quotes there saying that land use and land cover are really important, but I'm going to argue that we need to think about these uncertainties, especially as they're kind of all in these things. You know, they're all in the kind of different kind of frameworks for doing ecosystem services. This is our one, and what I'm going to argue is that understanding the uncertainties and the errors are important inputs in the data, are important inputs into your models. Okay, and so we just think about accuracy. Okay, without an accuracy measure, the map, any map, especially land cover and land use, is really an untested hypothesis. Okay, it's a pretty picture. And if we were to, you know, if you can do some kind of measure of, you know, a sort of observed and predicted, kind of correspondence matrix, we can actually, you know, we can generate sort of overall accuracies, and we can kind of get, you know, kind of map areas. So here we've got a map of class 1, which in this case was deforestation. But Olufsen, in this case, is drawn from Olufsen. What they showed was it's a 94% accurate map, but actually the actual area of deforestation was more than twice what was being recorded in the data. Okay. This has implications in another study. This was using the national land cover data in the US. If you didn't include the error, you'd sort of look at the ecosystem services value of wetlands in this case. It was just ecosystem services, I can't remember for what, you know, it was 1,000 billion a year from the map, but when it was adjusted for error, it was only 600 billion. Still a lot of money, but you know, the difference was by half. And similarly, for wetland value, it increased from kind of, you know, nearly 2 trillion to nearly 3 trillion when the data were adjusted for error. So error in your valuation of ecosystem services is critically important. You need to bring these in to your data. Okay, so I suppose what I'm going to argue here, coming back to some of the introduction I gave, is that the understanding what's getting represented is quite important. Here's a very old table from nearly 35, 40 years old nearly now, okay, from Townsend, and this is just showing you the different global estimates of different kinds of land cover and land use from 40 years ago. Hasn't really changed much now. With 40 years on, we still can't really agree about what's out there. And if you look at any of the global products, that 40%, I don't believe that. I think it's more likely 25. But you get very large differences in different products for what is out there. I don't see any of this getting talked about, because actually these are the data you're going to make your decision on. And if you think about why this happens, I'll give you one quick one. I want you to all just think about your favourite forest. Okay, just, there's my favourite forest. Think about where it ends and what kind of trees it's got in it. And you just think about it integrating into another land cover, land use, maybe a pasture, maybe a wetland, okay? And my argument is that you've all got an internal conceptual view of a forest. And there's a great website by G. Hyde Lund. He maintains, I think it's up to about 700 definitions of forest with hyperlinks. Okay, and if you just go and pull out two of the kind of dimensions, this was work done more than 10 years ago now, but if you just look at what forest definitions in terms of canopy cover and tree height, you get very different results. So Zimbabwe, 15 metres, 80%, Portugal, I'll come back to that one, 1.5 metres and 10%. Even the United Nations can't agree. Here's Forest Resource Assessment, there's UNESCO. Different bits of the United Nations have got different versions of forest. Okay, and this plays out. So are these forests. I won't take a big vote on it, but they're all maps. They're all kind of a bit weird. Yeah, okay, that one's probably expected. There's your Portuguese definition of forest. This is mapped because it's Forestry Commission in Scotland, been chopped down, still mapped as forest. This is not forest because it's Finnish and it's all about timber production and it's not growing quick enough. These are too dense. So it's not expanding quickly enough, so it's not mapped as forest. And if you kind of chase this through, just looking at tropical rainforests, okay, this is Forest Resource Assessment, and this shows you how the kind of concepts of forests have shifted around. Okay, here's tropical rainforest. Oh, I will see what I like with a car. Tropical rainforest, 2 words, tropical rainforest, 3 words, okay? And the mappings are quite interesting. Okay, so here you're kind of, what's the problem with tropical rainforest deforestation? It's growing, it's brilliant. Okay, but this is all to do with changing semantics. So do you know that when you plug it in? And a final example is bog. In 1990, the land cover map was generated by CEH, and it was done by scientists based on what they could identify, really, Robin Fuller and the gang. And they came up with some classifications. And in 1990, bog was defined in, if you like, on sort of water-loving species, basically. By 2000, we'd had the Rio Earth Summit, and we were now interested in habitats. And now bog was to do with peat depth, although it's still called bog. Okay, so we've got lowland bog and upland bog and bog. Now, consequences in one Ordnance Survey square, SK, my favourite one, from Glossop to Leicester. Okay, because it's got a bit of everything. And in 1990 there was 12 pixels of bog, less than a hectare, and in 2000 there's 75 square kilometres. Okay, and it's not just land cover land use, it also happens with sea level. Okay, some German and Swiss engineers built a bridge from 2 sides, and they missed by 0.5 metre because they hadn't thought about the fact they used different base measurements of sea level. Okay. Okay, so I think this is kind of where I've come from here on this one. Almost everything in geography, all spatial data, are a matter of abstraction. Okay, we necessarily have to simplify, aggregate the real world into our data, and there are choices about how we do that. And actually, your choices will depend on all kinds of things: who's paying for it, where you come from. Okay, if you've grown up in a BGS, you'll have a view of the world that is different from someone who's been at CH or the Macaulay Institute or something like that. The technology you use, ever new sensors, ever new measurement techniques, all of these things will change the data that comes out. Okay, and I think so I think this is one of my favourite graphics. It's not reproduced very well, but it's the pixel view of the world. It has square tractors, square trees, square cows, square bits of river. Okay, and there's a lovely paper by Fisher called The Pixel, A Snare or Delusion, a remote sensing letter from 1997. And I think there's some of these uncertainties. Pete and I worked a lot on these because we were working with uncertain land cover. We were trying to join together land cover data that was different. So when we talked about model coupling and inputs being different and having different assumptions, I would say that's semantics. Okay, if we all agree what it is, then that's great. We can wang through this as error and be dealt with by probability. Now, I know Peter would disagree wherever he is, but I think where we've got a disagreement over what it is we're measuring, when things are vague or ambiguous, then there are other approaches for handling that, not just pushing it into error, but explicitly reasoning with the uncertainty, almost in a three-valued logic. I also think if you want to kind of find out more with about these kinds of things, I recommend these to my students. Read these when you've got a bit of spare time. This is a book about essentially about categorization and classification, and this is a category of things in Aboriginal culture: women, fire and dangerous things. It's not all women at all times, and it's not all fire at all times, but it is, you know, a category of things. Science in action, if you want to understand how data and science are socially constructed, this is fantastic. And this is probably a book that's going to come back, because we're starting now to recognise that the art of drawing lines on a map that don't exist in reality is a limitation. And we should be thinking more about kind of continuous fields rather than discrete lines. Okay, thank you very much.